Ladies and gentlemen, all right, so this is going to be a bit of a long one, so I should let you know the goal up front is to demonstrate that if you use a sextant to navigate on Earth, then you have to accept that the geometry and the maths of it is derived from the Earth being a globe. So if you deny that, then you're going to have to come up with some other geometry if you think sextants work on a flat Earth. We all know flurfs suck at geometry, so obviously don't hold your breath. Right, so why the fuck are we starting with the Black Swan? So if the Earth is a sphere with radius 3959 miles, then every distance to the horizon can be no more than 1.22 times the square root of the observer's height in feet. Now this is a little bit of a detour, and it might take a few minutes, but I think it's important. So all I want to show here is where this 1.22 times the square root of the observer height formula comes from. So first of all, I think everyone already knows that this formula is just an approximation for the distance to the horizon, just like the 8 inches per mile squared is an approximation for curvature. But both formulas are accurate enough for any observation that we're likely to look at. Okay, so since the 1.22 is an approximation, what is the precise formula? So here I've represented the geometry with the observer at some height m above the surface, and drawn that green tangent line to the circle that represents the Earth. D is the distance to the horizon, which is the arc length rather than a straight line. Obviously the red lines are the radius of the Earth, and the angle between them I'm going to call A. Alright, and if we use radians for this angle, then we can simply say that angle A is equal to the arc distance D divided by the radius, because that's literally how radians are defined. All right, let's just switch that around to get it in terms of D, and we'll use that part later. All right, now, since the tangent to the circle forms a right angle at that point, we've got a right angle triangle, so we can also express that angle A using trigonometry. So we've got the adjacent side and the hypotenuse, which means we can use the cosine function. So the cosine of that angle A is the radius divided by the radius plus the observer height. So just apply the inverse cosine function to both sides to get it in terms of the angle. And then we just stick that angle back into the formula from step 2. And we have the precise formula for the distance to the horizon. Woohoo! Okay, so here is how you get the approximation. And to get that approximation, you have to make 2 simplifications. The first simplification is that the distance to the horizon, which is the arc length D here, is the same length as the line of sight from the observer to the horizon. All right, and now to work out that distance D, we've just got a right angle triangle, and we can use Pythagoras' theorem on that. So r squared plus d squared equals r plus m squared. Now we're just going to expand out what was in the brackets. So r plus m squared equals r squared plus 2rm plus m squared. Both sides have an r squared term, so we can drop it from both sides. Now this is the second simplification. So since the height above the surface is going to be really small relative to the radius, and we're going to square it as well, then it's not going to make much of a difference, and we can just drop it completely. Alright, so if we've got distance squared and we just want distance, then obviously take the square root of both sides. And now we've got a term in here which is the square root of the observer's height, so the square root of m. So let's just pull that out by itself for a second. All right, so up to this point we haven't actually specified any units. So we could have been working in metric or imperial, but now we're going to declare that the units are imperial, which means the radius is in miles, and we want the observer height to be in feet. So we have to divide it by 5280. So let's just move that 5280 over to the first term. And now we've got something that vaguely resembles the approximation from the Black Swan argument, where distance to the horizon is some number times the square root of the observer's height in feet. Yay! Well done to the flirts for keeping up. So now, when we plug in the radius of the Earth in miles, which is 3959, then that first term simplifies to 1.22459, which is where the formula comes from. Obviously it's been rounded down to just 1.22 for convenience. But how accurate is it? Alright, so here's a comparison spreadsheet. In the first column I've got various observer heights from 5 feet all the way up to 20,000 feet. In the second column is the distance to the horizon using the precise formula. And then just to show how accurate the approximation is, columns C and D use the 1.22 times formula, and they're about 99.6% accurate. And then in columns E and F, I've used the more accurate 1.22459 times formula, which as you can see is near enough to 100% accuracy. Okay, so thanks for indulging that little detour, and now we're back on track. On screen now is an excerpt from the American Practical Navigator, which was originally written by Nathaniel Bowditch, but it's been revised many times, and is now carried on board every vessel in the United States Navy. So it's basically the Bible of celestial navigation, and has been for close to 200 years. And this is the section in the almanac that discusses the correction you need to make because the horizon is not at eye level. So flirfs, you need to take your pick. Either the horizon doesn't rise to eye level, or celestial navigation doesn't need to make an adjustment for it. So you probably should just take the L on this one now, because if you're claiming that celestial navigation is accurate, then you need to make the correction for the horizon not rising to eye level. Anyway, there are a couple of little nuggets in this section. The first one I've highlighted here gives you the formula for a particular angle, and you might recognize it from the diagram I drew earlier. So the cosine of the angle AOD is the radius divided by the radius plus the observer height, which we then used to work out the distance to the horizon. And the angle they're talking about is this angle here, AOD. And if you passed geometry in year 5, you'd also be able to work out that this AOD angle is the same angle formed by BAC, and that angle is the angle down to the horizon that we have to correct for. But while we're here, I've highlighted another few nuggets. Firstly, that the line of sight between the observer to the horizon is bent by refraction. I've seen a few flirfs try to claim that this must be a straight line. So again, pick your poison. You can't just cherry pick your way out of it. Second nugget on this page is that the horizon appears higher due to refraction, which again flirfs have been denying for years. Thirdly, that the amount by which refraction changes the dip correction varies with changing atmospheric conditions. So applying something like 7/6R isn't going to be applicable under all situations. I'm sure you've heard me say it before, get well above the surface where the temperature gradient is more stable, and then refraction will be much more predictable. But the nugget I want to draw your attention to is this little one at the bottom. It's another approximate formula where the dip to the horizon D is in minutes of arc, and it's equal to 0.97 times the square root of the observer height in feet. Does that sound familiar, people? So going back a few slides, we showed that when we stuck in our radius value of 3959 miles into the first term of the Black Swan formula, that's how we got that constant number of 1.22459 times the square root of the observer height in feet. Well, we can actually play around with this equation as well and express it in terms of R. So let's square both sides and then just multiply by 5280 and divide by 2. And no surprise whatsoever, it spits out the radius that we put in, which was 3959 miles. So completely trivial exercise. But what I'm wondering is if we take the formula for horizon dip angle, which is 0.97 times the square root of the observer height in feet, what radius value do we need to put in to get that constant of 0.97? You know, will it be 3959 miles? I don't know. Let's work it out, shall we? So what we need is some kind of expression that when we stick in a radius value, we get 0.97. Just like when we stuck 3959 into the Black Swan formula, it gave us 1.22. So here's the 5th grade geometry again. The angle between the observer's horizontal and the horizon, which we've called A, is the same angle as the one formed by the 2 radii. And that's the angle that we're trying to quantify. And we're going to use the same simplifications that we did earlier, and that is firstly that the arc distance to the horizon is the same as the observer's line of sight, and secondly that that m squared term is going to be dropped. So the two things we're going to take from this is the distance to the horizon approximation, and also that we can use trigonometry on angle A. So the tangent of angle A is equal to that distance d over the radius r. Okay, so let's rearrange all this shit to try and get it into a form that looks like the horizon dip correction formula on the right hand side. So we're going to start with that simple right angle triangle. So tan A equals the distance over the radius. Now we're going to apply what's called the small angle approximation, which is basically if this angle A is small and measured in radians, then the tangent of the angle is equal to that angle. If you need to understand why this is, there's a pretty good explanation on Wikipedia. Right, so now we're going to substitute in our approximation for d, which we derived at the start of the video, and we get this pretty ugly equation. So let's tidy that up a little bit by bringing it all under the square root. And then we can get rid of one of the r's from both top and bottom, which is looking nicer and looking a little closer in form to our goal over on the right hand side. Okay, now the horizon dip correction is in arc minutes, but our angle is measured in radians. So to convert it to minutes, we need to multiply it by 180 over pi to get degrees, and then by 60 again to get it to minutes. Awesome. So now it looks like a bit of a monstrosity, but we've finally got it into a form that looks like our equation on the right, which means that this must be equal to our 0.97. Now I'm not going to waste any more of your time rearranging this formula, but if you solve this for r, you don't get 3959 miles, you get 4,758 miles. So I'm wondering if the Flurfs can remember any other situations where we might use a bigger radius than the 3959 miles. That's right. We use 7 over 6r in the curve calculator. Well done, guys. And if you're wondering, 4,758 miles is about 7.2 over 6r. And that is the radius that the almanac uses to calculate the horizon dip angle. All right, so let's recap what Flurfs have to accept if they think the sextant and celestial navigation is somehow proof of flat Earth. 1. The horizon doesn't rise to eye level. If the horizon was at eye level, you wouldn't need any correction for the height of the observer. 2. The line of sight between the observer and the horizon is curved. If it was straight, then the values in the correction table would be wrong. It's interesting here as well that the Flurfs seem perfectly fine to apply refraction corrections to the sun and the stars, but not to the horizon. 3. The geometry used to calculate the correction is explicitly derived from the Earth being a globe. It even has the diagrams. 4. The horizon itself is loomed up by refraction. So this is kind of tied into number 2, but just to be clear, if there was no refraction, then the correction would be even further below horizontal, which means the refraction effect is looming and not sinking. And 5, the horizon dip formula uses a radius pretty close to 7 over 6r, which kind of shows that it's being used in the real world and wasn't just pulled out of Mick West's ass. But that's nowhere near the biggest problem with celestial navigation on a flat Earth. What Flurfs don't seem to realize is that celestial navigation is just a generalized version of the Polaris problem that we've been beating you over the head with for the last few years. So instead of it being Polaris dropping 1 degree for every 60 nautical miles, it's some other star that drops 1 degree for every 60 nautical miles. Now I know all of the debunkers have already addressed this, but just in case you're a Flurf, you might need it repeated a dozen or so times before it sinks in. Right, so we all know that the angle to Polaris matches your latitude, and sailors have been using this fact to navigate for hundreds of years. So if you see Polaris at 60 degrees above horizontal, then you know that you are at 30 degrees times 60 nautical miles from the North Pole, which is 1800 nautical miles, and that means your latitude is 60 degrees north as well. And if the base of our triangle is 1800 nautical miles and the angle to the star is 60 degrees, then we can do some simple trig to work out the height of the star. And in this case, it works out to be 3,117.7 nautical miles. Now let's have another observer, and he sees Polaris at about 30 degrees above horizontal. So that makes his distance from the North Pole equal to 60 degrees times 60 nautical miles, which is 3,600 nautical miles. Again, we can do the simple trig to work out the height of the star, and what do you know, it's 1,000 nautical miles lower than where you just calculated it to be. And this is usually the point where the flurfs just declare that you can't do trig on stars, or that we don't know what they're made of, or some other irrelevant bullshit that makes no sense. Although I guess the good thing to come out of this sextant argument is that we've finally convinced the flurfs that we can look up in the sky to work out the shape of what we're standing on. Okay, so we've just seen how the trig fails on a flat Earth, and here's how it works on a globe. As you can see, it's utterly trivial to show that the angle to Polaris matches your latitude, and it also explains why you can't see it from the southern hemisphere, because there's a whopping great big lump of planet in the way. But as usual, the flurfs will just hand wave everything that doesn't suit their narrative, and just throw around buzzwords like perspective, as if it actually explains anything. So, with that in mind, I have a challenge. If this is the year of the sextant and it's the #1 flat Earth proof, then all I'm asking you to do is show two things. Number one, how do you derive the horizon dip correction if the Earth is flat? And number two, how do you derive the 1 degree per 60 nautical miles if the Earth is flat? I guess I will not be holding my breath for genuine responses from the flurf community.